Chapter 8, to your left, please. This is our illustration from page 325. And this is what I want to keep in mind when I'm thinking about my decisions about our hypotheses. In very much the same vein as with our confidence intervals. I am confident in the white areas. Confident that I've made a mistake if I'm in those shaded areas off to the side. So, for each confidence level, alpha, 1 minus alpha is our safe region. What we're looking for is some threshold, some critical value to figure out, keep the hypothesis in tension. So the thing I need to know most to make my decision is how do I find that critical value? What I'm really saying is that the mean that I find in my sample is too far away from the expected theorized mean in my null hypothesis for me to be confident in my answer. If it's too far away, I'm going to reject it. And too far away means in one of my shaded regions. The area of that shaded region is alpha, which is why if I go to make my test stronger, I make alpha smaller, fewer false positives, it's harder to reject, more possible false negatives. The dividing line is the critical value. I need a test statistic. Something I calculate. In our case, think about X, the X bar. And then I say, what kind of a distribution do I have? Because my type of critical value depends on that distribution. Wait a minute. What distributions have we been using in the last chapter for the stuff you just gave me? What distributions did we use? I used the normal one, or was the other distribution we used in this last chapter? Dan? Uniform was in the chapter before. Our T distribution, students T. And the normal one goes with Z. So that's what it's going to come down to. What distribution do I have? Do I know it to be a normal distribution where I get to use a Z value? Or do I need to use T with my degrees of freedom? Now, again, going back to that picture for a second. I said my hypothesis that we were dealing with on Wednesday was that people average 2 energy drinks. And I said, that's my hypothesis. The average is 2. That's that middle kind, where I'm saying my null hypothesis is equal to. The alternative hypothesis is it's not equal to. I don't know if it's going to be too low or too high. If I said the average person drinks fewer than 2, then my hypothesis, less than 2, is the safe area. More than 2 is the problem area. That's a right tail test. So we need to know which kind we're dealing with. The critical values for one tail tests are smaller numbers than the critical values for two tail tests, because it's the same area in here as in here, as in both of these put together. So two tail tests are more difficult to reject. You have to be further away. So what's the question? Z versus T. How do I know? How do I know whether I should be using Z or T in my distribution? Not just any standard deviation, which standard deviation? Because there are two of them, right? There's S and there's sigma. Which one do I need to know? I need to know the population one, sigma. Equivalently, I could know the variance. But all the variance is sigma squared. So if you tell me you know the population standard deviation, I'm going to use the Z table. Or if it says anywhere in the problem, the most amazing word for all of that, normal, because the Z is the normal distribution. If it says normal, I'll use that. If it doesn't say the word normal, or if I don't know sigma, then I have to approximate sigma, and I use S instead of sigma. That's where I have to use a t-test. So that's the dividing line. Do you know the standard deviation of the whole population? Let's try one. I want to try and test a mean where I know the sigma. I need a test statistic. I need to know, well, I've done a sample. I want to compare that sample to the overall behavior, right? All right, wait a second. I'm going to try and put this on my standard normal distribution. What's standard normal conversions? I got to standardize this data. What I need is a Z. I'm using a Z table, so I should find Z's. I'm going to call this the calculated Z value. I wrote the word CALC underneath that, the calculated Z value. This is my test statistic. And that's the thing I'm going to compare to my critical number. Gee, how do you get a Z value? There's a formula for that. Wait a second. The Z takes the number we got, subtracts the mean we think we want, divides by, except now that I'm doing a sample, I'm going to divide by the standard error instead. So what I do is I take the sample mean I got, I subtract it from the subtract from it the assumed mean, and I divide by the standard error. How do you do standard error? Oh, that was the one with the square root thing in it, right? So that's the standard deviation we were given, because it says right up there at the top of the screen. I know the standard deviation, and I divide by the square root of n. And this is our Z-calc value. Okay, wait a second. I'm asking how far off from my assumed value is the one I got from this group. And I want to be confident that that difference is small. What I'm really asking for is, does the confidence interval around this number contain 0? Because if the confidence interval contains 0, then I'm confident that my sample and the thing I think it should be are the same. So now I need to decide what my confidence is. Most of the time, we're dealing with 90% confidence intervals, 95% confidence intervals, or 99% confidence intervals. Remember that our confidence interval was 1 minus alpha. So if my alpha is 0.1, that's a 90% confidence interval. If my alpha is 0.05, that's a 95% confidence interval. If it's 0.01, that's a 99% confidence interval. Okay, wait a second. I need half of each of those numbers. And then I go all the way back to the normal distribution table. So turn to Appendix C. Let's look at our normal distribution. Go to table C2. I'm going to start with table C2. Find for me the area, not the z. Find the area, 0.10. The closest thing to 0.10 you can find. Say again? Aha. 0.10. 0.01, 0.02. Here we are. 0.1003, way down here, goes with negative 1.28. Now that would be the area in the left end, right? Look at the picture at the top of table C2. That would tell me that the left tail has an area of 0.1 when z is negative 1.28. So I'm going to say that that's the left tail. Z equals negative 1.28. What if I want the right tail? Well, all I have to do is turn that picture over, don't I? Because the left side and the right side are the same. So the right tail is going to be positive 1.28. I'm leaving a space in the middle on purpose. Space in the middle is for two-tail. Now, if it's two-tail, then I don't need the area to be 0.1. I need the area to be 0.05. Find me the area closest to 0.05. Clearly, that's going to be a number that's more negative than negative 1.28 because we want a smaller area. We're shifting further to the left. Aha! That's right between 1.64 and 1.65, so I'm going to use 1.645. But notice, half of it's on the left, half of it's on the right, so there are actually two numbers for the two-tail test. That middle number looks awfully familiar, doesn't it? I've seen that one all over the damn place. We're going to use those a lot. Okay, let's repeat the process. We just did 0.05, didn't we? We came up with 1.645. When the alpha was 0.05, that means that right here is z equals negative 1.645, and over here is z equals positive 1.645. How convenient. We already got those numbers for free. What area do I want for this middle value? That's the z. The area should be 0.025, right? And if we look, 0.025 has a box around it. That's how often we use that one. It's got a box around it in the table. Son of a. Now, unfortunately, neither the left tail or the right tail for the 99% one are 1.96 because that's 0.025. I need a value in the table of 0.01. It's going to be between two numbers. And it looks like it's closer to 233 than it is 232. So if we interpolate, we'd go 2/3 of the way. So I'm going to use negative 2.236. And up here, I'm going to use positive 2.236. 2/3, 0.666, right? So we'll just use that. The one in the middle, I need 0.005. Again, it's going to be between two numbers. There's no zero in there. The 7 is so 257 and 258. So if I split the difference again, it's plus or minus 2.576. Now I am 100% certain looking this crap up on the Z table is a pain in the neck. So at the top of page 228, I have all of them written down exactly like this with little pictures to go with them as well. But I wanted to prove to you, page 328, that these didn't fall out of thin air. We didn't make this up. We pulled it off that Z table on purpose. Okay. With that in mind, I can now ask the question, if I'm doing a left tail test and my Z calculated is too far down, then I'll reject. If I'm doing a right tail test and my Z calculate is too big, I'll reject. If I'm doing a two tail, then it can be either too big or too small. So we usually take the absolute value and say, is the absolute value too big? But now I have a decision rule. Gesundheit. I'm going to call these numbers in the table here, I'm going to call them critical values. So I'm going to write Z crit. That's my decision-making number. The critical number is the boundary between the two regions. So if my calculated number is too small for a left tail, reject. For a right tail, if the calculated number is too big, we reject. And for a two tail, we take absolute value. So that's my decision rule. Now I know what to do to determine if my hypothesis is correct. I survey the room. And I did this last on Wednesday when I asked, how many of you drink energy drinks? And y'all looked at me like I was out of my damn mind. Okay, I'm going to say in this room, the number of average energy drinks consumed a day is 0. If I said it was 2, I'd need the standard deviation to be able to figure out what my critical value is, right? And what my calculated value is. And then I'd be able to say whether I was too high or too low or just plain wrong. Page 332, number 17. Green Beam Limited claims its compact fluorescent bulbs contain no more than 3.5 milligrams of mercury. Mercury is a poisonous heavy metal. If there's too much mercury and you drop a bulb and break it, you have to cut away the carpet and dispose of it as if it was hazardous material. You should never vacuum up a broken fluorescent bulb. You put mercury vapor into the air, you inhale it. It's a bad thing. Okay, I go take a sample of 25 bulbs. I take a sample of 25 bulbs and I get a sample average of 3.59 milligrams of mercury per bulb. Now, the statement from Green Beam was that their bulb contains no more than. What kind of a test should I be doing? Say again? They're claiming it's less than a number. The problem would be if it's too big, that would be a right tail. So it says here, write the hypothesis for a right tail test using their stated value as the assumed value. For a right tail test, what's my null hypothesis? Everything is hunky-dory, they're okay. How do I write that down? Not yet. I'm just writing up the hypotheses. I'm not testing anything yet. I need to know what I'm trying to test. I have to have a hypothesis to test it. If they are right, then the average I should get should be how in comparison to 3.50? Less than or equal to. And the alternate hypothesis, if they're wrong, strictly greater than. I can't do Z-calc yet because I'm missing a piece of information. What other piece of information do I need to do the Z-score? I need a standard deviation, which they didn't give me yet. But it says in the very next part of the problem, oh, the manufacturing process has a known standard deviation of 0.18. With this piece of information, give me a Z-test statistic. What's Z-calc? even before I do anything on my calculator, I'm going to write down all the setup. I take the number I got from my observation, I subtract the expected average, I divide by the standard error, so that's the 0.18 over the square root of how many observations I did? 25. So now I know what to calculate. What'd you get for an answer? Now I need to know what confidence we want to have. So I can ask, we're doing a right tail test at a 1% significance. Do I accept or reject the null hypothesis? Do I reject or not reject the null hypothesis? Okay, wait a minute. Significance is alpha. Alpha equals 0.01. That's 1%. Do I reject or not? So at alpha is 0.01, I need to know what's the critical value. That's off the table we just looked at, 2.236. Our value is too big. According to our value, the confidence interval I would make around 2.5 doesn't contain 0, which means the difference between the expected average and the average I got is too big for me to believe them. What do I say to the company? Your light bulbs contain more mercury than you claim. You are in durance vile of EPA regulations. You are now fined a giant pile of money for making bulbs with more mercury. Naughty, naughty, naughty. Now, they could come back and say you only took a sample of 25 bulbs. Maybe you need a larger sample. You only took a small sample out of the infinitely normally distributed population. Maybe we should take a bigger sample and do it again. Maybe I need to do it more than once. All of those are possible responses. But if I'm the guy running the business, I'm going to be doing this on my own before the EPA shows up and finds my ass. Questions?
Will it always be on the table we got?
If it isn't, I need to do the same thing we did to get those values off the table, right? I need to look for the right area and backfill what's the Z value. That's more of a pain in the neck than it's worth, so almost all the time, I'm going to use one of those table values. But I can do this in Excel.
If this problem is for for us not to reject it, it would have to be the exact.
Oh, if they gave me a two-tail, then I would have to either be bigger than the number or smaller than the negative version.
So it couldn't just be.
Right, it's not an exact match, it's a comparison. That's why here, in all of my decision rules, there's an inequality. So if it was a two-tail, the number for the two-tail is 2.576. If it was a two-tail, we would have passed. I wouldn't be able to reject the null hypothesis. I'd say, oh, no, that's within the margin of error. I'm good enough. But our critical value was smaller because we did a one-tail. Because of the way they said the hypothesis, we contain no more than 3.5 milligrams. I'm on the normal distribution, right? Table C, let's go to C1, C2. C2. Go find 2.5 on table C2. Yeah. If I think of Z equals 2.5, there's some area here, right?
0.0063.
Yes. Now, the way you get that off the table in table C2 is to use negative 2.5 because you're looking to the left side. Look at the picture on table C2. The picture on table C2 has the shaded area to the left. We want that really small one, so we flip this picture over. But that's 0.0062. That number is a probability. Yes? That's the chance that my average would be that big compared to the average I expected. This is a probability. That's the chance that the mean is actually way out there. Now, I said I would be okay with a 1% level of significance, right? The decimal for 1% is 0.01. Notice this number, the chance of Z being bigger than 2.5 is smaller than 0.01. You told me how significant we were trying to be, and this is too small. I'm going to call this a p-value. And that's related to my significance. If the p-value I get is smaller than my significance level, then I reject. Now, that's for a right tail or a left tail. What if I'm dealing with a two-tail? But probabilities are always positive numbers. Think about the picture for the two-tail. The picture for the two-tail, what do you notice about the areas shaded in the two-tail? It's alpha over 2, not alpha. So the easiest way to do that is to double this number instead. I want to compare not just the probability, I want to compare twice the probability for a two-tail. The p-value tells me the chance that my mean could be that far off randomly. There's only a 0.6% chance that you would randomly get a number that high, 3.59, if your average really was 3.5. And that's too small of a chance for me to be comfortable with it. I'm no longer confident that this happened randomly. In other words, that small of a chance couldn't just be blind ass luck. There's got to be something going on under here. Page 329. Here's a picture. When we calculate that probability, we're calculating a number between 0 and 1. And Matt, that's what I meant by probabilities are always positive. Probability is always between 0 and 1, right? So if my chance of getting this number is so small that it couldn't have happened randomly, given our mean and standard deviation, then that does not support our null hypothesis, and we should reject. If the p-value is anything bigger than the chance for our critical value, then I'm okay. But if the probability is smaller than that, then it is very unlikely that this just happened to occur. An airline serves bottles of spring water that should contain 10 ounces. Problem number 23. They should contain 10 ounces. With a standard deviation of 0.07 ounces. In problem number 23, they give me 12 randomly chosen bottles. I'm going to cover this up for a second. Here are my 12 randomly chosen bottles. Notice there's a data file for this. So you can go to Excel, you can download this data file from our chapter files on chapter 9, and you can get all these numbers. And then you can compute the average. And you have the population standard deviation. You were given sigma. So you test these 12 bottles. And when you test these 12 bottles, you find out that the average is a little bit more. It says in the text, set up a two-tail hypothesis to test the filling quality controls at the spring water company. So it tells me to do a two-tail. Two-tail hypothesis. I need H null, my null hypothesis, and I need the alternative hypothesis. Yes, but before I actually do a test, I need to know what I'm accepting or rejecting with my test. So that's the rule for making the decision. But the decision is between these two things. So what am I deciding between in a two-tail test on an average? Either I think the average is what they say it should be, or it isn't. Those are my two choices. It either is what we thought or it isn't. Now, it also tells me at 95%, right? Oh, no, it says it the other way. At 5%. At 5% significance. Test this. So now I can do what you just said, but I need zcalc, and then I can compare it. So what is zcalc? And what is zcrit? One of those you have to do some work for, the other one you just look up on a table. What's the value of zcrit? %, two-tail, 1.96. What's the calculated one?
Were we given
Yes. How many bottles did we do? It's in the problem. There were a dozen bottles. I didn't write it down, though, so good catch. N equals 12. What's that number? At least 2 decimal places. Hey, wait a minute. That's a positive number against the absolute value of this. What do I do? How do I make the decision? Those are the two numbers I'm comparing. The zcalc versus zcrit. What am I supposed to do here? Reject or not? If the critical value is bigger, if the calculated value is bigger than the critical values, I reject. This one's inside, I don't reject. For Monday, I want you to do one more thing for me. I want to know the probability that Z was bigger than 0.784. That's our p-value. We'll do that one, that version of this on Monday. Have a wonderful weekend, everybody. I will see you then.